Yes, now in this class we will discuss about how the bending moment diagram and shear force diagram can be drawn for different load cases on a simply supported beam. Here, before that, we will define what do you mean by BMD and SFD. Bending moment diagram, it is a diagram representing the values of bending moment at different sections of the beam. Suppose if this is the beam, AB is the beam, if you want to have at different points or sections of the beam the values of bending moment, after calculating that, we can plot them in the form of a diagram. That diagram is called as bending moment diagram. Similarly, the diagram representing the values of shear force at different sections or points of the beam, it is called as shear force diagram. This is very important in the design subjects also. Once you identify what are the sections, the values of bending moment is maximum and values of shear force is maximum, whether it is positive or negative, then you can decide about the dimensioning of the structures. So that is very important. So that is why BMD and SFD we should know how to draw for different load cases in the case of simply supported beam as well as cantilever beam. So the profile, how the diagram will be, the profile of BMD and SFD, it always depends on the type of the load acting on the beam. So different types of loads act on the beam, point load, UDL, triangular load or UVL, external moment may be acting. So depending on different types of loads, the profile, how the diagram will be, that is decided. So normally how to plot is, we are going to take the axis of the beam as horizontal, and above that horizontal line, if the values are positive, positive values are plotted above the line and negative values are plotted below the line. That is the geometrical representation of BMD as well as SFD. Of course, it need not to be scaled. Now, let us discuss how the BMD and SFD will be for different load cases on a simply supported beam. Now, I will take first the central point load. AB is a simply supported beam carrying a central point load W. Central point load means it is acting at a distance of L by 2 from either supports. Total span is L. In that case, bending moment diagram will be a straight line. It will be a straight line and the maximum bending moment will be at the center of the beam. Actually, these derivations I have explained in my Google class, so you can just refer to them. Okay. Now, here, how to plot that? So, since we have got positive value WL by 4, positive value, we have to take above this line AB. So, it's a straight line. So, bending moment diagram is a straight line in the case of a point. Before drawing the bending moment diagram, we need to calculate the reactions. As I already told, reactions have to be calculated using the equilibrium equations. Using that, we can calculate that the reactions are equal to W by 2 here. Since the beam is symmetrical, the load is equally distributed between the supports. Total load is W acting at the center, that is symmetrical beam, therefore reactions will be equal. So the value of bending moment at C you can easily calculate. So just see the left side, so W by 2 is the reaction multiplied by L by 2. So that is the moment. Since it is acting upwards, so as I already told in the last class, upward forces give positive bending moment. W by 2 to L by 2 becomes WL by 4. That is the value of bending moment at C. Even if you take right side also, you will get the same answer. W by 2 into L by 2. Right side also upward gives positive bending moment. So whether you take left side or right side, it gives the same value. Similarly, shear force diagram. Now I will just give you a very simple way of drawing shear force diagram. So what you have to do is you have to start from that point A, draw the horizontal line AB, which represents the axis of the beam. Now from at point A, you have an upward reaction of W by 2, move upwards by W by 2. Then there is no force from A to C, so shear force remains constant. So draw a horizontal line. That means from A to C, shear force is constant. At C, you have a downward force of W. Come down, move down by W. That means already you are W by 2 upwards. So therefore, another W by 2 you have to take downwards. That is negative side. So then from C to B, there is no force. therefore shear force remains constant. Then at B you have an upward force W by 2. So finally it joins here. So it starts from point A, ends at point B. So please keep it in mind that whether it is BMD or SFD, the diagram should close. It should start from the first point and it should close at the last point. That is the basic check. So this is the bending moment diagram and shear force diagram for a central concentrated load acting on a simply supported beam. Now suppose if the load is not acting at the center, it is acting somewhere else. So I will take the distance as A and this distance as B, so that A plus B is equal to L. In that case, if you calculate the reactions using the equilibrium equations, you will get WB by L as the reaction here, WA by L as the reaction here. Now if you want to calculate the bending moment at C, see to the left side, that is WB by L into A. So that means it is WAB by L. So whether you take left side or right side, you will get the same answer. Here also the bending moment is positive. Maximum value of bending moment occurs at C here. Here also maximum bending moment occurs at C. So please note this. So this maximum bending moment occurs at C. Here also maximum bending moment occurs at C. And this is also a straight line because it's a point load. Now coming to shear force, you start from A, move upwards by WB by L. Then from A to C there is no force, so horizontal. Then from at C you have a downward force of W, so move down by W. So totally you have to move down by W. Then from C to B there is no force given, so therefore shear force is constant. Then at B you have a reaction WA by L upwards. So the diagram will close here. It starts from A, it closes at B. So please see the difference between these two. Central concentrated load maximum bending moment is WL by 4, whereas it is simply somewhere else, then it is WAB by L. Whereas shear force will change at that point where the concentrated load is acting. So this is about the SFD. Now coming to the third case, uniformly distributed load. So if the load is uniformly distributed, it is shown like this. I have taken small w per unit length. UL means unit length. It may be meters or centimeters, whatever it is. So it is unit length. So now I have marked C here, which is the midpoint of that beam. L by 2, L by 2. Now in this case, the total load is W into L and reactions will be equal because it is symmetrically loaded. WL by 2, WL by 2, they are the reactions. Now if I want the bending moment at C, see to the left side, so WL by 2 is the reaction, WL by 2 multiplied by L by 2 minus this is acting downwards. See, so this when you are calculating bending moment, this UDL should be converted to concentrated load, and when it is converted, it acts at the midpoint of that span. So that means you have to take this as L by 4 and this value will be WL by 2 because WL is the total load. So from here to here, the total UDL is W, but over a length of L by 2. Therefore, concentrated equivalent concentrated will be W into L by 2. So if you calculate the bending moment at C, it will be WL by 2 into L by 2 minus WL by 2 into L by 4. If you simplify that, you will get WL square by 8. Okay, so there the maximum bending moment occurs at C, at the mid span. Now coming to the shear force diagram, so WL by 2 is the reaction acting here upwards, start from A, move upwards by WL by 2. Then what you have to do is, if a UDL is given, shear force linearly decreases. So how we have to take that is, total shear force from here to here, that means total load from here to here is W into L, W into L. Already you are WL by 2 here. So I have to come down because the load is acting downwards. I have to come down here. How much I have to come down? WL I have to come down. Already I am there here WL by 2 positive. Therefore negative also I have to come WL by 2, so that this total from here to here, the difference is W into L, and if you draw that, since it is symmetrical, at C the shear force will be 0. This is a very, very important point you have to note down. Bending moment is maximum where shear force is 0. So that point you have to note down. So in this case, it's a special noted point. So in all these, you can see that at A and B, bending moment is 0. Why? Because if you take this point A, if you see left side of A, nothing is there, no force is acting, therefore its bending moment is 0. And as a property of simple support, moment is 0 at a simple support. So that is why at A and B, bending moments will be 0, but it may have shear force. Now coming to the fourth point, fourth case, it is the external moment. Suppose for a couple is acting on the simply supported beam, depending on whether it is clockwise couple or anti-clockwise, the reactions are calculated. Here, since there is no external force acting, only it is subjected to only couple, one reaction acts upwards, another reaction acts downwards. So they are numerically equal, but they are acting in opposite direction. See how to take these reactions is, he has given a clockwise couple here, reaction should be anti-clockwise, it should be like this. So that means, if you take these two reactions, here downwards, here upwards, these two will form a couple in the anti-clockwise direction, that is the reaction. So this is why I have to take. Suppose if it is anti-clockwise given here, M by L will be upwards, here M by L will be downwards. So if anti-clockwise couple is acting on the beam, reaction should produce a clockwise couple. That is the idea behind here. Now here, when you draw the BMT here there is no bending moment here. As I already know, at A it is 0, at B it is 0. At simple supports, bending moments are zeros. Now, when you come to C here, now I am here. There are 2 points I have to take. One just to the left side, another just to the right side of C. When a moment is acting, you will be having 2 values of bending moment at that point. So if you take left side of the C, and you will be getting M by L into L by 2. M by L into L by 2 will be negative here because it is downwards. Left side downwards I am taking. So M by L into L by 2 becomes M by 2 here. So it is a negative, therefore I have taken point like this. Then at here, if you take right side if you take, then M by L into L by 2 upwards, that is positive. So right side of C, you have a positive bending moment of M by 2. So both the values you have to plot at C only. So since I am moving from left side, first I have to plot this negative sign, minus M by 2, then plus M by 2. The total here will be M, which is equal to the moment given at that point. Then join them by a straight line. So it is a straight line. So profiles are very, very important. Whereas here you can see, here I forgot, this is a parabola. WL square by 2, WL square by 8 is the maximum value here. It is a parabola here. In the case of a UDL, it is a parabola. Coming to shear force diagram here, start from point A, come down by M by L, and from A to B there is no force given, only moment is given. You should not consider that moment when you are drawing the shear force diagram. So it becomes constant from A to B, and at B you can see there is an upward reaction of M by L, so it closes. So this is that means entire shear force is negative from A to B here. Whereas bending moment is negative from A to C, from C to B it is positive. That means hogging effect is there here, sagging effect is there here. Whereas shear force is negative throughout. Suppose if anti-clockwise couple is given, the only difference is here this reaction will be upward, this reaction will be downward, and here positive will come first, negative will come next. That means the diagram will be like this and like this and like this. And here shear force will be completely positive. So that is the difference between anti-clockwise couple and clockwise couple when they give BM and SFP. Just it is reverse of that. Next, the fifth case is uniformly varying load or the triangular load. So it is having maximum value at A and 0 at B. So it is linearly varying. So uniformly varying load, or it is also called as triangular load. So reactions, after finding the reactions from using equilibrium equations, WL by 3 you are going to get here, WL by 6 you are going to get here. See, observe that here reactions are equal because beam is symmetrical, here reactions are not equal. So higher load is there this side, therefore reaction is more here, reaction is less here. So if you calculate the maximum bending moment, in this case you are going to get at the point C at a distance of 0.423 times L from this edge, or at the distance of 0.577 L from this case. That means from the 0 edge it is 0.577 L. From the maximum intensity edge it is 0.423 L. At that point you will get shear force 0. So where shear force is 0, you have the maximum bending moment, that is at C. And the values I have given here. So shear force diagram, WL by 3 upwards here, reaction upwards. Then here WL by 6 downward. So negative here, therefore it is downward. So therefore you have to join here. The very important thing is it is a parabola. It is a cubic parabola here. See the difference here. So in the case of UDL and UVL, you should be careful, because in the case of triangular load and external moment, you are not, in the case of concentrated load and external moment, you need not worry because everything is a straight line. Whereas in the case of UDL, bending moment diagram is a parabola, shear force diagram is a straight line. In the case of triangular load, bending moment diagram is a cubic parabola, shear force diagram is a parabola. So where shear force is 0, at that point you can have maximum bending moment. The value of maximum bending moment is this much, 0.0641 WL square. Actually this is a book one which I had explained in my Google class. This is a very important derivation. So you have to note down the values here. So that derivation you have to practice. Now I have given here mainly lastly what are the different profiles of BMD and SFD for different types of loads. Whether it is simply supported beam or cantilever beam, only the profile depends on the type of load. If it is a point load, bending moment diagram is a straight line, shear force diagram is a straight line. If it is UDL, uniformly distributed load, bending moment diagram is a parabola, shear force diagram is a straight line. If it is a triangular load or UVL, then bending moment diagram is a cubic parabola, a shear force diagram is a parabola. If it is an external couple or a moment, bending moment and shear force diagram both are straight lines. So this is a very important topic wherein I have explained how the profiles are there for BMD and SFD for different types of loads acting on a simply supported beam. In the same manner you can get for cantilever beam also. Thank you.